Okay, in this cast, we're going to be talking about error. It's important to understand the types of error and the difference between random and systematic error, especially when we do lab write-ups. Okay, so we're going to start with understanding the difference between a theoretical value and a measured value. Okay, so the theoretical value for pi, okay, the ratio between circumference and diameter is 3.1415, and this repeats forever. Okay, but if you were to measure this, like we'll do in an activity, you get something like maybe around 3.14, but this is not exact, of course. Okay, you cannot get an exact number. You always have some error with the measurement, so always have some error. Okay, so what's the causes of this error? So we have to kind of talk about this. Okay, so the first almost good kind of error, in a way, that you can't get away from is called the random error. And this is error from small variations in measurement. If you measure the circumference of a circle, the length of the string might change a little bit. It might be warmer outside, so it might be more elastic. Who knows what it is? But there's all these small, variations that make your measurement imperfect. Okay, and so you can, if you repeat the trials, you can reduce this, but you can never completely eliminate random error. Okay, so and it's usually unbiased. It means that you didn't do it on purpose, and it affects the precision. Okay, so 3.14 is less precise than 3.1415, blah blah blah. Okay, so in a activity like this, the example could be, the string stretch could be one example of a random error. Another one could be the circle, shape. Maybe it's not perfectly round, so there's a little bit of error due to that. And another one is maybe instrument capability. Okay, so maybe the instrument's not 100% precise, which actually can never be. So that's part of random error. Now, a bad type of error is called systematic error. Okay, and this is it's bias, means some people you would do it on purpose, or you're using poor equipment, and this affects the accuracy. Okay, so for example, in this scenario, if you were to use a ruler that had inch markings on it, and you were thinking in centimeters, then you would get a very bad measurement. Okay, so examples of this is faulty equipment, or ruler in this case. Ruler. Okay, and so you get an incorrect reading with systematic error. Bad. Okay. Also, another little skill we need to look at is how to estimate uncertainty. Okay, so as you can see, not the greatest resolution in this picture, but if you have an instrument that has extra markings, you should get a more precise measurement than if you have a ruler without as many markings, like this one. So maybe in this case, you can say, oh, this nail is 4.4 centimeters. Okay, and so the rule is we estimate to one extra digit of precision beyond finest marking. Okay, so this has markings of 1, 2, 3, 4, 5. So we know it's 4 for sure, and then we would guess this, which is maybe 4.4. Okay, so this is the last guess. It signifies how precise this instrument is. Okay, in this case, we can see that it has more fine markings. So in this case, we can say maybe this nail is 4.43 centimeters. Okay, the idea is this instrument is more precise, so we have more decimal points. Okay, so the precision of the instrument is implied in the significant figures of your measurement. Again, two other common values that we compute that I wanted to mention is percent difference, which compares the difference between two lab values in maybe two different lab groups. Okay, so if you have value 1 minus value 2 divided by that average of the two values times 100, you get percent difference in the values. Sometimes in labs, we want to report the deviation between a theoretical value and an experimental value. So this could be like, okay, if you measure value for pi of 3.14, but the actual value is 3.15 and so on, you want to know how far off you are from the theoretical value. Okay, and so this is called percent error. And the way you calculate it is experimental minus theoretical divided by the theoretical value times 100. That will get you the percent error.